Good morning, folks. So we are going to start one more section before our next quiz. We're going to spend a few days on this one. So I'm not thinking about a quiz until probably Tuesday, maybe Wednesday even, next week. And it's going to be on 5-1 through 5-3. So 5-3, the last section that's going to be covered on this quiz is something called improper integrals. What makes an integral improper versus proper? So an improper integral can be a lot of different looks. We're going to cover them all one at a time, but the most common version of an improper integral is where the upper or lower limit of the integral is defined as either infinity, or if the lower limit was negative infinity, that would be considered improper. Now, not every improper integral has a value, has an actual numerical value. So we kind of have to break this down conditionally. So we can't operate with infinity. Infinity is not actually a number, right? It's just kind of a concept of increasing without bound, but it's not a number we can plug in and operate with. What we can do, though, is we can work with limits as we approach infinity. So it's nice that in our very last chapter of calculus for the year, we kind of circle back to our first chapter in calculus and revisit the concept of limits. So you might want to look up some notes on limits from back in chapter 1. But what we can do is if we treat b, this variable, kind of like a placeholder for a number, right? And we define it as some real number, and then we're going to take what's happening to my integral as the limit of b approaching infinity, what becomes of my integral. And there's two things that are going to happen. The limit as b approaches infinity either exists or it doesn't. So if the limit exists, it is a real number. I feel like this is a little blurry. If the limit hits a real number, then the improper integral is convergent, or we say converges, okay? And it would converge, you would say that this integral equals whatever the numerical limit is, okay? If you can't tell, I was running out of ink on my blue marker. If the limit does not exist, meaning either it literally does not exist, or the limit approaches infinity or negative infinity, which is not a real number, then we have the improper integral is diverging, divergent, or it diverges. Okay? So I only have two examples real quick for you, one of each of these cases. So we're going to do evaluate. We'll start with we'll start with one of them and we'll figure out which case it is. The improper integral 1 to infinity of 1 over x squared. Okay, I put the dx in the numerator, but this is essentially 1 over x squared. So the most important part here is going to be setting up with proper notation, right? So we're going to say now that we're going to change the upper limit to this b placeholder and take the limit of my integral as b approaches infinity. Okay, if this limit exists, great. Whatever the value of my limit is becomes the value of my integral and it converges. If this limit doesn't exist, the original integral diverges. From here, we're just going to integrate like we would always integrate, but we're going to do it with respect to this variable b. So 1 over x squared, we can apply it, make it x to the negative second, and we can make it a power rule, okay, which the antiderivative of 1 over x squared is negative 1 over x. All right, and according to our theorem from calculus, we're going to plug in our upper limit b and our lower limit 1. Now keep in mind, b is part of my limit notation. So if you recall from limits, yes, this limit notation has to come down every single line. So even after we plug in b and we plug in 1, we see this here. And we're going to continue to evaluate this limit notation as b approaches infinity. Okay, obviously negative 1 over 1 reduces, and we have the double negative making it positive. Now here's where we can actually evaluate my limit. 1 over b, as b approaches infinity, this term is going to get smaller and smaller, and it will approach 0, which is a good thing. Anytime you can get an expression to approach a real number, you're one step closer to the original thing converging. So because that approaches 0, we can now finally drop the limit because we've evaluated the limit at 0. This other one is a constant, and my limit exists. My limit is 1, and the original integral converges to a finite area of 1, which let's just talk about this. This is essentially the area under the curve, right? We talked about this when we introduced integrals. The area underneath the curve 1 over x squared from 1 till forever has a finite area, even though it goes on forever and ever, which is kind of mind-boggling to kind of get a hold of. But it is interesting because what happens is this curve gets so close so very quickly to the x-axis that you're adding almost no area as you go on and on and on and on. So it does approach +1 as an overall sum. Now, let's find another example. Obviously, process of elimination, we know kind of what's going to happen here. So we're going to take the improper integral 1 to infinity of 1 over x. And again, I just put the dx in the numerator. So I set my notation up here for my limit of the integral 1 to b as b approaches infinity of 1 over x. Now 1 over x, very common antiderivative. We might recognize that as ln, okay? So again, we're taking down the limit notation step to step. We're going to evaluate this antiderivative at b and at 1, okay? And ln of 1, natural log of 1 is 0, so that's very nice. Natural log of b is, we don't really know because b is a placeholder, right? But as b approaches infinity, natural log of b is still going to approach infinity, right? Natural log is an increasing function. It doesn't really have any bounded horizontal asymptote. It's going to keep going up, sometimes very slowly, but it's going to keep increasing. So it approaches infinity, which is not a real number. Thus, the limit diverges and the improper integral diverges. Or we could say the improper integral is divergent. Okay? So this was a brief introduction. We're going to work with a couple different looks and a couple different types of integrals throughout section 5.3 for the next couple days before we take a quiz in the early next week. So go back on the course page. You can get started on the homework if you so wish. I tried recording this earlier, and my sister actually called me because my 7-year-old niece wanted to tell me a joke she read in the book about math. So I have to treat you guys to it because I'm a very proud uncle. And she said, "What do you call a chicken who loves to count her eggs?" A mathema chicken. I'm going to leave you to your laughs. Good day.